Okay, so in this video, we will discuss the vibrational mode. For you to understand the vibrational modes, you need to understand the molecular vibrations first. A molecule as a whole, it will either be translated or rotated. So there will be a translational motion or rotational motion as a whole, while each atom has its own motion. So if we're looking at the single atom, it will has in its own motion, but if we're looking at the molecule, then it will as whole molecule will be translated or rotated. Now, vibrational modes, they can be either IR active or Raman active. These are your two bands for a mode to be observed in IR spectrum. There should be a change in the permanent dipole. For diatomic molecules, they are observed in the Raman spectra and not in the IR spectra. So permanent dipole, if there is a change in permanent dipole, it will occur in the IR spectrum. If there is a diatomic molecule, then it is in the Raman spectrum, because the diatomic molecule have one band, and no permanent dipole, and therefore there is only one single vibration. You can take example of a linear molecules like O2 or N2. However, unsymmetric diatomic molecules do absorb the into the IR spectra. We're going to look at these in the detail later. Right, so for now, the normal modes of vibration, these are your asymmetric vibration, symmetric vibration, wagging, twisting, scissoring, and rocking. So these are the 6 normal modes of vibration. Then we move on to the calculation part of the vibrational mode. For you to understand this, you need to understand the degree of freedom. Degree of freedom is the number of variable which is required to describe the motion of a particle completely. For example, for an atom moving in a 3D space, 3 coordinates are adequate, so its degree of freedom is 3. So the motion is translational. If we have a molecule made up of n number of atoms, the degree of freedom becomes 3n, because each atom has the 3 degree of freedom. So you understand now where this 3n came from. Now, furthermore, since these atoms are bonded together, all motion are translational. Some becomes rotational and some others vibration. Remember, we discussed 6 types of vibrations. Okay, now we look at, there are linear molecules and then there are non-linear molecules. For the non-linear molecules, all rotational motion can be described in terms of rotations around the 3 axis. So the rotational degree of freedom is 3, and the remaining will be 3n minus 6 degrees of freedom constitute the vibrational motion. Then for a linear molecule, so the formula for the non-linear is 3n minus 6. Then we look at the linear molecules. For the linear molecules, rotation around its own axis is no rotation, because it leaves molecule unchanged. They are linear, so there are only 2 rotational degree of freedom. For any linear molecule leaving 3n minus 5 degree of freedom for the vibration. So the formula is 3n minus 5 for the linear molecules, and for non-linear molecules 3n minus 6. N in this case is the number of atoms within the molecule of interest. Remember, these are the formula we look at to calculate the vibrational modes of any molecule. Now, there are 3-step procedure to calculate the vibrational mode. First step is to determine if the molecule is linear or not. You can do what you can do is you can draw out the molecule using the VSEPR. So you can understand whether the molecule is linear or not, but you should have enough practice to see a molecule and say if it is linear or not. Then next step is calculate how many atoms are in one molecule. For example, CO2, here there are 3 atoms, 1 carbon atom and 3 oxygen atom. So we said how many atoms? There are 3 atoms in carbon dioxide molecule. This number here, when we calculating the number of atoms in the molecule, this is your n value. For the linear molecule, we use 3n minus 5. For non-linear, we use 3n minus 6 formula. Then when we have this n value and we know whether the molecule is linear or not, then we're going to plug in this n value and solve for the vibrational mode. For example, here there is an example question: how many vibrational mode are there in the linear carbon dioxide molecule? So the question is already saying that it is linear. Then we know that it is the linear molecule, so step number 1 is already done. It's given in the question. Then step number 2 is to calculate the number of atoms in the molecule. So CO2, carbon 1, oxygen 2. There are 3 atoms, so we know this is linear, 3 atoms, and we know what formula to use for the linear molecule, which is 3n minus 5. Then we plug in the 3 value in this 3n minus 5, which will give you the 4. So the vibrational band for the carbon dioxide molecule is 4. Now there is a trick to this. When you look at carbon dioxide, we already told you carbon dioxide is 4. Ask yourself a question: if I give you a molecule SO2, this is similar to CO2, whether the SO2 will have same 4 vibrational bands like CO2 or not. What do you think? The first step you're going to do to solve for the SO2 is to find out whether the SO2 is linear molecule or non-linear molecule like carbon dioxide. There are 3 atoms in here, there are 3 atoms in here, right? So don't get confused. First step, always remember to follow to see if the molecule is linear or not. If the molecule like SO2, which is not linear, then what you're going to do, why it is not linear? Because SO2 contains a lone pair which cause the molecule to bend in the shape, whilst carbon dioxide, it doesn't have any lone pair. So you're going to plug in the number of atoms in the non-linear formula: 3n minus 6, 3 times 3 minus 6, 3 times 3, 9. Then minus 6 will give you the 6 modes of freedom for SO2 and 4 modes of freedom or vibrational bands for the carbon dioxide CO2 molecule.